All right, since the lecture today is a short lecture, only 50 minutes, rather than starting a completely different topic, which was going to be latent variable models, very fundamental for machine learning, but I thought since we finished the last lecture talking about generalized linear models, maybe I thought I should give you some extra elements of this topic, okay? So this follows, I think, chapter 9 from Murphy's book, in case you want to read more about it. Okay, I indicated that this family of, the exponential family that we used, or I refer to at least several times, includes many distributions. And you see here, it goes from the beta and the gamma distribution, the Dirichlet distribution, the Gaussian, the multinomial, the Poisson, etc. But there are lots of important distributions like, mixtures of Gaussian, Laplace, student T, etc., that they are not parts of the family. So what I want to do is I want to take a more fundamental look today at the exponential family. So see some of the things again that we discussed before, and then I want to see if we can generalize practically everything we learned up to now for regression and classification for the exponential family type of distributions. So the discussion is going to be a little bit esoteric because it's going to be things that they don't look very familiar, but you have to trust me. This is a very fundamental topic in machine learning because most of the algorithms are really based around this exponential family and the resulting generalized models. Okay, so a formal definition of things that maybe I threw them in slides here and there. So what is the exponential family? It's a family of distributions that has this form that you see on the first equation, okay? So it's a distribution on X that has parameters theta, and these particular functions that you see there are very essential. So for now, I'm only going to introduce eta as the natural parameters of the distribution and u of x as the sufficient statistics. And I'm going to explain with one or two slides later on why u of x is called sufficient statistics. Now, the only thing I'm going to say, when you write a distribution in this form, these parameters theta are not the parameters that you affiliate distributions with, which usually are moments. All right, they're different set of parameters, not the moment. So if you write a Gaussian, it's not going to be in terms of the mean and the variance, for example, if you try to put it in this form. That's why eta, we call them the natural parameters, and somebody will say, why do you call those natural if I never hear them in courses? Well, that's another story, okay? They're very natural because you will see this form will allow us to generalize things in a significant way. Okay, let me introduce, so g of theta here and h of x are additional functions. So I'm going to introduce this function a of theta that is minus log of g. I want you to remember a of theta because we're going to make use of it today. So that way I can put g of theta inside. So another equivalent form of this exponential family is h of x times the exponential of theta transpose u minus a of theta, where a of theta is minus log of g. Now, let's look closer to what g of theta is, right? So if we assume that this distribution is normalized, so the integral of the whole distribution is going to be equal to 1, you can immediately see that g of theta defines the normalizing factor of that distribution because it doesn't involve x, right? So g of theta is that function of the parameters that normalizes the distribution. So effectively, if you introduce another terminology here, if you introduce the normalizing factor as g of theta is 1 over g of theta. And because by definition a was minus log of g, a will be the log of z, and z is known in statistical mechanics as the partition function. So we know that this normalization factor, right, has importance in model selection, but it is fundamental to many other problems in machine learning and statistical mechanics. And actually what makes most tasks difficult is because computing this A or computing this Z, it's a very difficult task. And you can see here, if I write A of theta to be, by definition, the log of the partition function, and Z is 1 over G, all right? And G is, so G is this integral. So effectively, the A, or log of Z, is the log of this integral. So not only you have a log, but you have an integral in X, and X can be very high dimensional. So you can immediately see computing Z or A, it's not an easy task. But you know, if you search a little bit, you will find out that many fundamental properties, let's say in statistical mechanics, are requiring the calculation of this partition function. So it's not decorative because it normalizes the distribution, but it has essential properties that we're interested on. Okay, so I want you to remember this is the form we're going to use. I am actually going to cut and paste this formula in many slides so that I remind you constantly today what it is. We introduce A minus log of G, and the normalization factor is 1 over G. And so an equivalent form for this exponential family of distributions is the formula on the bottom. All right. Now, lots of times, this natural parameter theta depend on other parameters theta. All right? So up to now, when we write distributions, we always write them in terms of parameters theta. So if, if you see something that looks like this, but is affiliated that eta is a function of theta, it's a little bit different from what we did before. Before, theta maybe was the mean or the variance, but now, when I introduce theta in this form, it implies, all right, that is affiliated with the exponential form of the distribution, where we have this natural parameter theta, all right? It's not just any parameters theta, all right? They are the parameters that define the natural parameters eta that give me this exponential form of the distribution. So again, if you see theta in any of the slides, the dependence on theta comes through eta. And eta doesn't have to be the moments or anything like that. And we will see infinite examples in the follow-up slides. All right, this slide actually, it's very technical, so I am not going to cover it on details because it requires some ideas from probabilistic graphical models, another course that I taught only once here. So let me just read you the conclusion. Any joint probability distribution over discrete random variables lies on the exponential family. So if you take the joint distribution of any set of discrete variables, you get actually an exponential family, a distribution in the exponential family. So now you can see how powerful this is, right? Any set, if any distribution over discrete variables can be written in the exponential form, and the slide actually shows you with, I think you should read it. I just don't want to go through it because it requires a factorization that is being introduced in another course, but you can see in 3 steps, you can actually produce, you can write the distribution in any of these equivalent forms for the exponential family. Okay, so I am not going to do this in any ways. We talk about continuous distributions. So let me give you some examples. So I'm going to take the Bernoulli distribution and see how it can be written in terms of this natural parameter theta. So I remind you the Bernoulli distribution. This is the heads, tails type of experiment with probability mu getting heads. So x can be 1 heads or 0, right? So the distribution is mu to the x, 1 minus mu to 1 minus x. So what I'm going to do is I'm going to do some manipulations of this to show you that you can write it in the exponential form. So can I write this actually as e to the log of the whole thing? Can I do that? Right? So if you write e to the log of the whole thing, and you expand the log as x log of mu plus 1 minus x log of 1 minus mu, you can write it like this. And simplifying further, you can immediately finish and say, this is the final form. So you can see you have an exponential of this times x. So what is this thing inside the brackets? I'm sorry, not just the brackets, but the log of mu over 1 minus mu. That's the natural parameter zeta. So the natural parameter zeta is log of the mean of the Bernoulli distribution divided by 1 minus mu. And this is g of theta. That's the normalization factor. And I remind you what's the general form, right? So there is no h of x in this case, but you can see eta is this log, all right? U of x is equal to x, and g of theta is 1 minus mu. So, I give you the results also for a of theta on the bottom, all right? So a of theta, remember, is minus log of g of theta, and g of theta, it's 1 minus mu, but you have to write mu in terms of theta. So mu in terms of theta is the logistic regression function. So eventually you get this nice result on the bottom. Okay? So no big deal. We put the Bernoulli distribution in the exponential family form. But I want to start commenting on the following. You notice here that the natural parameters are defined uniquely in terms of the mean of the distribution. So the relation between mu and eta in this case is 1 to 1. And this is not an accident, as we will see, because I'm going to prove it, all right? So the relation between eta and mu is 1 to 1, and so mu is the logistic function of eta, and this, the inverse function, eta as a function of mu, is called the logit function. Both of them very popular in machine learning. Again, you may say they come by accident, but in this life, you know, nothing is accidental, okay? So again, this is my eta, and you can see you can invert this and write mu in terms of eta, all right? So you have eta in terms of mu and mu in terms of eta. Okay, you can take another distribution. You can take, for example, the Poisson distribution that is given like that. And again, if you put exponential of the log of this, and you write, you can see that u of x is x, eta is the log of lambda, all right? A of theta is lambda, and immediately you can see if theta is log of lambda, lambda is e to the eta. And remember, for the Poisson distribution, lambda is the mean of the distribution. So again, you can invert uniquely the natural parameters with the mean of the distribution. If you take the multinomial distribution, all right, things get a little bit murky. So let me, remind you what the multinomial distribution, right, is. So you have m states, all right, and the probability of hitting any of those states is mu k. So this is what the distribution looks like. So if you write this as the exponential of the log of this, you're going to get exponential. The log of this will give you a summation. So immediately you can see that the parameters theta are this vector that consists of these logs of mu k. And the vector x is, the u of x is just the vector x, okay? Now, no big deal. The multinomial distribution fits nicely with the exponential family, but immediately notice there is no a of theta there. A of theta appears to be 0, okay? So we must not be doing something properly for a of theta to come to 0. So there is something wrong with this slide. And what is wrong is, given on the bottom of the slide, these mu k's are not independent of each other. All right? If you say I have mu1 probability to hit state 1, mu2 state 2, the sum of this is equal to 1. So there are only k minus 1 independent states. So to put this multinomial distribution to the exponential family form, we need to account for this constraint. Okay, so we need to redo this from scratch. So how do we do from scratch? You remember I mentioned we are going to we're going to write this as the exponential of the log of this. All right, so we do that, but we split the log to a summation here over the m minus 1 state. And for the m state, what do we do? For mu m, we write it as 1 minus all the other mu's. And for the x mu, we write it as 1 minus all the other xk's. So that way it becomes a probability over k minus 1 states. Or, I'm sorry, m minus 1 states. All right? So I'm not going to do the algebra, okay? So this is how the distribution is written, where we keep summations over m minus 1 states. So when you finish things, it comes out the following nice result, that eta k, so the natural parameters, are log of mu k divided by this summation. And the thing on the denominator, you agree with me, is mu m, capital M, right? Because of the rule that all of these sum to 1. So in principle, I can define actually eta mu as well by calling this mu m, because mu m over mu m gives me 1, so log of 1 is equal to 0. So this formula still applies if you extend it to k equal 1 to m, okay? So eta is written like that. This is the natural parameters for the multinomial distribution. And with some simple algebra, you can invert it, and you can write mu in terms of the natural parameter theta. And I want you to look at this function at the end of the slide and tell me if it reminds you anything. Does that function remind you anything we have seen before? The softmax, right? And somebody will say, but I don't remember having 1 there. Yeah, but if you put exponential of eta subscript capital M, that is 1. So that's the softmax function. So again, is that coming out of nowhere? It's for you to think. Accidents, again, don't happen, right? But it's nice that suddenly you see going from the natural parameters to these moments mu k, somehow the softmax function comes out. So in summary, this is the relation between eta and mu. This is the final form, so the function g of eta is given by this. A minus log of g is given by that, okay? So we can write a multinomial distribution in its exponential form using natural parameters, all right? Just remember, you need to account for the constraint that the sum of these mu k's is equal to 1, okay? And once you do that, a doesn't come to be 0, okay? A is the log of this summation over exponentials. And by the way, this expression, log of a sum of exponentials, all right? It appears very often in machine learning. And it is, I mean, if you search on Murphy's book, you will see there is a special algorithm that is being used to compute this carefully, okay? So it's not just you do simply a summation there. So you have to compute this carefully. Okay. I am not going to do the gamma and the beta distributions. You have to trust me. If you take the beta distribution and you do the same trick, you can immediately see that the essential statistics are log of mu and log of 1 minus mu. The natural parameters are a minus 1 and b minus 1. And everything at the end of the day fits naturally to the exponential family that we have seen. And the same thing about the gamma distribution. All right, how about the Gaussian? Now, the Gaussian, somebody will say, it's already in the exponential family. Yes, it is, but it's parameterized in terms of the moments and the variance, right? And in terms of the moments and the variance, everybody knows what the Gaussian is. Now I'm going to give it to you in terms of the natural parameters, and you're going to say, but it doesn't look very good. That's maybe why this is never used. But I have to tell you, this natural form of the Gaussian has properties that allow you, for example, to multiply Gaussians much easier than multiplying Gaussians in the form of using these moments. Okay? So if you do the algebra, all right, can somebody look at this equation and tell me what is u of x? What are these, what I call the sufficient statistics u of x? So you remember here in my general form I have eta transpose u of x. So for the Gaussian, what is the sufficient statistics u of x? So what is u of x? I mean, look at the form that x comes, right? So what u of x has to be is x and x squared. And immediately, actually, you can start thinking why I call this sufficient statistics, right? Because to calculate the parameters like the mean and the variance, you know, you need to know x and x squared, all right? So, so u of x is x and x squared, and the coefficients on the front is the parameter theta, all right? And g of theta is given by this rather complicated form. H of x, there's no x, it comes from the normalization of the Gaussian, and a as minus log of g is given by this nice form, okay? So immediately you can see that in this form of the exponential family with natural coordinates, natural parameters, the Gaussian doesn't look very appealing, all right? But I want you to remember it maybe doesn't look very appealing, but it may have properties that you will never get with the moment parameterization, okay? So again, you have to keep these results handy because when you have to do calculations using the natural form of the Gaussian, this is what you have to use, okay? All of these formulas. And again, where all these results come? Well, they come by trying to make this distribution to fit in this form, nothing else, all right? So u of x, x squared, all right? Eta transpose the coefficients, and obviously you can see the terms that I mark here with blue, all right? They involve the parameters mu and sigma, so obviously this have to be substituted in terms of the parameters eta 1 and eta 2, and that's why you get this complicated, otherwise looking result, okay? Nothing fancy. Okay, don't want that. Somebody may ask then, can we actually, how easy is to put a multivariate Gaussian in its exponential natural form shape? So can, you know, if you remember in, if you look at the exponential of multivariate Gaussian, written in terms of the precision matrix lambda, it takes this form, right? There is, you know, okay? There is a quadratic term, there is a linear term, and there is a constant term, and of course there is a normalization term that I'm not showing to you. So, without doing much algebra, you can see that the natural statistics, obviously, it's x and xx transpose, which makes sense, right? So what you do is, to define the vector u of x, you take the matrix xx transpose and you transform it to a vector, right? So you take every column, one column after the other, and so you form this vector. So u of x is really a combination of x and the vector corresponding to xx transpose. And immediately you can see that the natural parameter theta is basically the transpose of this matrix, so lambda times mu that you see in this term. And then the other natural parameter is the matrix lambda, but you have to put it in a vector form, all right? Because our formula requires eta transpose, where eta is a vector, times u of x, where u of x is a vector. So here is u, here is eta, and the rest of the calculations you can see on this slide. Complicated, okay? But you know, the Gaussian fits the exponential form, right? And usually when you think of exponential distributions, immediately the Gaussian goes to your mind, but this family, it is written like that, so you have to do some work to actually put it in this form, and that work is on at the end of this slide. All right, now there was a result that I showed you on the previous lecture that I told you have to trust me, but now I'm going to prove it. And this result is extremely important and applicable to any of these distributions. So what is that result? So let me just state the result. The expected value of the sufficient statistics is the gradient of A. All right? So you remember how we define A is minus log of G. All right? So now it says the expected value of U is the gradient of A. For any of these distributions, so you can actually go and test this formula for any of the previous results, right, in all the other slides, and you can see that the expectation of U, all right, so if U is just X, the expectation of X, the mean of X, is the gradient of A. All right, how do you get this extremely powerful result that is applicable to all of these distributions? Very easy. This distribution is normalized, which means the integral in X is equal to 1. So start with this formula on the top and take the derivatives of the left and the right-hand side with respect to the parameter theta. So remember what the distribution is, right? So if you take derivatives of this integral with respect to eta, you have a derivative from G, which is here, and then you will have a derivative a contribution coming from this exponential. So this will give you the exponential times U. Okay? So effectively, you get two terms. Gradient of G times that plus G times this equal to 0. Now, on the first term, if I divide by G and multiply by G, I'm going to have gradient of G divided by G, and then I'm going to have the integral of the actual distribution. G times this is the distribution integrated, and that is equal to 1, right? So if I multiply and divide by G, one term will look like this, and the other integral is going to be equal to 1. And on the right-hand side, what do I have? I have G times H times this exponential is the distribution, times U integrated in X. What does it give you? If you have a distribution times U of X dx, what do you get? You get the expectation of U of X. All right? I mean, G times H times this, by definition, is our distribution. So multiply with U of X and integrate in X is the expectation of U of X. And there is the answer, because you remember A is what's the definition of A? Is minus log of G. So what's the derivative of A? It's minus 1 over G times the gradient of G, right? So this minus gradient of G over G is gradient of A. So a wonderful formula that is applicable to any problem. The gradient of A is the expectation of U of X. Can actually tell me if this formula, do you have any sense if this formula actually will allow me to keep going and compute higher order moments? Can I find the variance of U? What do you think? In other ways, if I take now, the same procedure and start taking second derivatives, what do you think I'm going to get for the second derivative of A? So the second derivative of A is going to turn out to be the covariance of U of X. So effectively, if you know A, you know all the moments, right? You know everything you want to know for the statistics, basically, of U of X. It contains all the information, and you can compute all of these moments by differentiation. So again, I'm not going to do the algebra, but if you use that the gradient of A is the expectation of u of x, and you take one more derivative, immediately you can see that you actually get the covariance of u of x. Okay? And you can keep going, and these formulas are for any distribution from the exponential family. If you have A of theta, which you do, right? You can search to Wikipedia any distribution you want and say what is A of theta, it will tell you. Second derivative, it gives you the covariance of the sufficient statistics. And since we have this formula, let me point something extremely important. So the covariance of U is a matrix, right? All right? I mean, in general, if U is a vector there. So is it positive, definite? What is it? I mean, you can even take the case of U being a scalar. Let's take the simplest case, U being a scalar. So is the covariance of U of x positive, negative? What is it? Positive. So the gradient, the second derivative of A, is positive. So the function A of theta is convex. And what does that mean that the function is convex? Does it have any implications? All right? So it does have implications. All right? So the implications are, if you look at the formula we derive, that the expectation of u of x is the gradient of A, the fact that A is a convex function means that, so remember, the expectation of u I call is the mean, right? So I call it mu. So the fact that A is a convex function means that given eta, I can find a mu, and given mu, I can find an eta. The function is invertible. So there is a unique relation between the moments and the natural parameters for any of these distributions. So what I stated before, right, with examples, now we can see it generalizes, and it comes from the fact that this function A of theta is convex, okay? And the mapping mu of theta, right, if you look at mu as a function of theta, is invertible, and it allows you to compute eta from mu and mu from eta. All right, which means if you have a moment parameterization, which is the way we introduce distributions, you can immediately find the natural parameters in a unique way. And if you start with the natural parameters, which usually we don't do, you can find the moments from there uniquely. Okay. Let me, before I proceed and tell you more fundamental properties for this exponential family, let me just put a word and explain what does sufficient statistics means. So this requires a little bit of ideas from conditional independence relations that you usually learn in probabilistic graphical models. But can you guess, when I say u of x is the sufficient statistic, what does that mean? What do you think it means, just conceptually? So you remember we have these natural parameters theta that maybe they are themselves functions of some other parameters theta, which I indicate here. So when we say u of x is the sufficient statistic for theta, just to make your life easy, what does that mean conceptually? So, in some problems, right, you want to estimate the parameters theta, you collect data x, and I'm just telling you the sufficient statistic for theta is u of x. So what does the word mean? If somebody asks you, what is a sufficient statistic? So you can calculate theta. The only thing you need is u of x. You don't need x. So you can think, for example, if you try to calculate the mean of a Gaussian, and I give you samples x1, x2, xn from the Gaussian, you don't really need the samples. What do you need? You need a sample mean, right? So basically, u of x, that's why it's called sufficient statistic, right? It is the only thing that you need from x to compute the parameters theta. And I'm going to write this formally in this wonderful relation that has lots of meaning. So the probability of theta given u of x and x is the probability of theta given u of x. Can you immediately see that conditionally given u, you don't really need to know x to compute theta? Okay? And if you want to actually get some imagination on the, start thinking about this conditional independence relations with graphs. So I introduced these dependencies with these arrows, all right? So x defines u of x, and u of x uniquely defines theta. So effectively, theta only depends on u of x, and u of x depends on x, right? So the arrows goes this way. So if I give you u of x, you don't really need to know x to compute theta. All right? So if I give you u of x, right, that's why this is plotted dark area there, right? If I give you u of x, you don't really need to know x to compute theta. And mathematically speaking, I write this equation as you see on the bottom. Actually, in frequentist statisticians, so this is the Bayesian way, all right? Because you can think of this probability being the posterior of theta given u of x and x. Now, frequentist statisticians, they don't use posteriors and the likes. So what actually they do is they invert the arrows, and they write these dependencies like that, okay? So I want you to look at this equation and tell me with words, what does it say? This is, again, we will not ever do this in Bayesian statistics, but it sort of, it tells you a different philosophical way of thinking of what u of x is. So here, if you take the conditional distribution of x given u of x and theta, this, so this probability of x with given u of x is independent of theta, right? So you can immediately see here the relation. I mean, the meaning is the same, right? U of x contains all the information about theta, so I don't need it there in the dependence. But this is a weird way of putting it because, what are you going to do with the probability of x given u of x and theta? But it contains sort of the same message as the posterior that we saw in the earlier slide. Now, there is another result that goes around this concept of independence and this probabilistic model. So looking at this graph, right, the concept that I introduce is that u of x depends on x and theta depends on u of x. If you take other courses that don't exist, you can, don't exist on Notre Dame, all right, you will learn that these dependencies here imply if you try to take the joint distribution of all three variables, you can actually write those as a function that involves x and u of x and a function that involves u of x and theta. And this is what is called the Niemann factorization, okay? And so this, just the definition of this sufficient statistics as we introduced, it actually implies that the joint distribution of the three variables is some function of u of x and theta and some other function of x and u of x. Again, this is fundamental theorem that you will learn. And somehow, the message that I want to pass here is that this idea of sufficient statistics implying this factorization is directly related with the form of the exponential family of distributions. You can actually see that if effectively we have a parameterization that is similar to what you see up there in the exponential family, and that's why u of x is the sufficient statistics, okay? Because, if you have a parameterization like that, then u of x is the sufficient statistics. It goes both ways, okay? So the fact that I kept calling this u of x, it comes from the description I gave you that u of x is what is needed to describe theta, but that by itself implies a factorization of the joint distribution that looks like that, okay? And really what we have with the exponential family, we have such a factorization. Okay. There's a lot of there for you to chew, but I have to tell you a little bit of these ideas. Okay. Let me generalize now some of the things we know, and I am going to compute the maximum likelihood estimate for the exponential family in general. For all of these distributions, given some data x, x1 to xn, I want to compute the MLE estimate of the parameters. But now this is going to be the MLE estimate of the natural parameters, right? So they will not be the MLE estimate for the mean and the variance, but of eta. So what do we have? We have n data points. All right, I just put capital N there. Mistake. So if I multiply my exponential distribution for each of my samples with sufficient statistics u of xn, you notice all of these exponentials will lead to a sum over all the u of xn's. You see that? All right? So if you take logs of this, you're going to have a summation over this h of xn, and then you're going to have n times log of g of eta, and then eta transpose times that, okay? So when you look actually for the log likelihood, right, you can immediately see that the sufficient statistics now become basically this summation of u of xn, right? That's the only information that you need to compute the parameters eta. So what's the maximum likelihood estimator? Is the one that does what? By definition? What is the MLE estimate of the parameters eta by definition? Are the parameters that do what? They maximize what? The log likelihood, right? All the likelihood. So I'm going to take derivatives of this with respect to eta. So on this term, I'm going to get minus n times the derivative of a. What's the derivative of a? I know, but I prove a fundamental theorem before. The first derivative of a is the mean, mu, okay? So is the expected value of u, okay? So the gradient of a is the expected value of e. So I have n here. I put n on the other side. And the derivative of this will give you this summation. So this is an amazing result. For all of these distributions, again, for all of these distributions, it tells you that at the maximum likelihood estimate, the expectation of the sufficient statistics is exactly equal, right? Is exactly equal to the empirical mean of these sufficient statistics u of x. I mean, we proved something like that, right, for the Gaussian, but just now I prove it for any of these distributions. Which means if you want to calculate, the mean of the distribution, you don't really have to find the MLE estimate of the parameters. Because this mean matches exactly this, right? So this matches exactly that. Now, of course, since this becomes now the expectation of u, you can potentially invert this relation and compute from this and the function of gradient of a, you can compute the MLE estimate of the parameters. But the bottom line is, if you are interested to compute the mean, right, you don't need to compute eta. You can directly use this relation, and this relation is universal for all of these distributions. So this is a very general result for distributions for the MLE estimate from the exponential family. Now, I give you a simple example for the Bernoulli distribution, okay? I think it was in slide 2. I summarize again how the exponential form for the Bernoulli distribution looks like. So remember, this is the coin example. So either I have heads, x equal to 1, or tails, x equal to 0. So the sufficient statistics is really the indicator function that x equal to 1. So at the MLE estimate, the true mean, all right, is the empirical mean that you see here. It's like if you do n experiments, the true mean is how many times you got heads, okay? Once you compute the true mean, all right, you can actually compute the parameter theta at the MLE, and they are given by log of mu over 1 minus mu, where mu bar is computed by the formula that you see on the second line from the bottom. Okay, so again, you can calculate the moments directly from this empirical mean, and once you have this for the moment, you can actually compute the natural parameters at the MLE estimate by inverting. Remember, there is a unique relation between the moments and the parameter theta. So if you have that unique relation, which is here is given by log of mu over 1 minus mu, you plug in the MLE for mu, and then immediately gives you eta for the MLE. Now, this slide doesn't belong here, but I want to say something about it, because for those who read papers in different subjects, like in machine learning, in deep learning, etc., they will come up across this and they will not know what it is, okay? So let me just, since we talk about the MLE estimate and maximizing the likelihood, let me introduce the following idea. First, let me introduce what's called the empirical distribution. So let's say that I have a true distribution, and the only thing that I am given are capital N samples. So the empirical distribution is basically a distribution that has these delta functions at the samples weighted with 1 over n. Right? So hopefully when you learn Monte Carlo methods, someone told you about this empirical distribution. So it's delta functions centered around the samples, okay? That's what we call the empirical distribution. So here is something extremely fundamental that people don't even talk about it. They take it, naturally. They start directly with this result. If you want to maximize the likelihood, all right, so if you want to find the parameters that maximize the likelihood, it comes out that this is equivalent to minimizing the Kullback-Leibler distance between the actual distribution and the empirical distribution of x. Okay? And the proof, for those who don't know what this is, and we will see it again later in the course, the distance between two distributions is written explicitly here. So one of these terms doesn't depend on the parameters theta, and the other term is this expectation of log of p with respect to the empirical distribution. So if you plug in these delta functions, you will evaluate basically that this term comes to be minus 1 over n times the likelihood. So if you want to minimize this distance, is the same as maximizing the likelihood. So I only mention this in passing here because people who do maximum likelihood, somehow they may throw you out of your thinking, because they will start by saying maximum likelihood, minimize this KL distance. It's the same problem. And actually, if you think about it, it's a more elegant way, because minimizing the KL distance, there's lots of nice algorithms that go with it that you don't necessarily affiliate with maximizing the likelihood. Okay. I don't have time I have to stop somewhere here. So let me just say, I'm going to try for on Tuesday, since we started on these generalized linear models, to say things about the priors, to tell you how you actually compute posteriors and predicted distributions for the exponential family, and a little bit about the maximum entropy distribution. And then I want to discuss how we can use, how we can bring generalized linear models together with the exponential family to do a whole class of problems both for regression and classification. So I'm going to repeat sort of, but with a little bit more technicalities. All of these things we learned up to now for regression and classification for the exponential family. So not just Gaussians, but all of these distributions. So we'll do a little bit of that on Tuesday, and then we will move on to latent variable models.